This buffer solutions are special type of solutions which is formed, and to this if we add a small amount of acid or base, its pH won't change. Which is the weak acid here? Acetic acid. And which is the weak base here? NH4OH, that is ammonium hydroxide. So this gives the salt which is a buffer solution. Here the solubility will be S itself, here the solubility will be 3S, and in the power you will have a 3 as well, right? So S into 3S cube, that will be 27S raised to 4. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today I am back with the last session of the chapter Equilibrium, that is session 9 of the chapter Equilibrium. So in the last session we discussed how to derive and show that the pH plus pOH is equal to 14, as well as pKa plus pKb is equal to 14, and ionization constant for weak electrolytes, as well as the different types of salt we have discussed in the last session. So in today's session we are going to discuss what is buffer solutions, which is easy and which is very important, right? And the different types of buffer solutions, as well as another very important topic, that is common ion effect. What is solubility equilibrium of sparingly soluble salts, solubility product and solubility product constant, solubility product expression, as well as what is ionic product. All of this we are going to discuss in this session. By that we will come to an end to this chapter, right? So first let us discuss what is a buffer solution. So let's see. These are solutions which can resist change in their pH value even by adding small quantity of an acid and a small quantity of a base. So these are special type of solutions. This buffer solutions are special type of solutions which is formed, and to this if we add a small amount of acid or base, its pH won't change. It shouldn't happen, right? If you are adding a small amount of base, means the pH value should increase. If you are adding a small amount of acid, means the pH value should decrease. But these buffer solutions has the ability to not make this change, right? Because some reactions are taking place in this buffer solution, so that the pH value will not change. So these are the solutions which can resist the change in pH even if we add small amount of acid or base. So how does this happen? So here the buffer solution, we have taken the example of acetic acid CH3COOH as well as CH3CONA, which is the sodium salt of acetic acid, right? So this is a mixture of these two which forms a buffer solution, that is a weak acid and a salt. Okay, so this acetic acid, what happens to this? How does it dissociate? Acetic acid CH3COOH dissociates into CH3COO minus and H plus, right? CH3COO minus and H plus. Now the salt, how does it dissociate into Na plus and CH3COO minus, right? The salt dissociates into CH3COO minus and Na plus. So now what did we say? If you are adding small amount of acid or base, what will happen? Some reaction will take place in the buffer solution itself and it will neutralize this effect so that the pH value will not increase. So for example, let us say small amount of strong alkali is added. That means we are adding a base. Little amount of base means OH minus we are adding, means what happens? The acetic acid has been dissociated into H plus and CH3COO minus, right? So the OH minus which is added to it, it will combine with this H plus and form water, right? So if it is forming water, what will happen? Of course the pH will not change, right? Because the extra OH minus which is being added, now it combined with, that is, it formed a reaction with H plus and forms water. Right. Now let us consider small amount of strong acid is added. Acid is added means H plus is added. So if extra H plus is added, what happens? In the salt, it will dissociate it into Na plus and CH3COO minus, right? So this H plus will be taken by this acetate ion and forms what? Acetic acid. So what happens? Again, the acetic acid is what is already present in the buffer solution. So of course the pH will not change again. So this is how the buffer solution works, right? I hope it is clear. Now moving on to the different types of buffer solution. So the first one is acidic buffer. An acidic buffer is a mixture of a weak acid and its salt with a strong base, right? So as you can see, CH3COOH, this is a weak acid, and you have CH3COONA, which is a salt which is formed with a weak acid and a strong base. Which is a strong base here? NaOH. Okay, so this is a acidic buffer example. Now you have basic buffer. Basic buffer is a mixture of, yes, it will be a weak base and its salt of a strong acid, right? So which is the weak based ammonium hydroxide, NH4OH is a weak base, and ammonium chloride, it's a salt with a strong acid. Which is a strong acid? HCl. So HCl and ammonium hydroxide will form the salt ammonium chloride, right? So this mixture gives you basic buffer. Another one is neutral buffer. So neutral buffer will be a solution of a salt made up of weak acid and weak base. So which is the weak acid, weak base salt? You can see CH3COONH4. It's a salt which is made up of a weak acid and weak base. So which is the weak acid here? Acetic acid. And which is the weak base here? NH4OH, that is ammonium hydroxide. So this gives the salt which is a buffer solution, neutral buffer solution. So I hope it is clear to you. Moving on to the next important effect, that is called as a common ion effect. So from the name itself you can tell something is common here, that is a common ion is present here. So what is that? We are going to study in detail. Let's see the definition first. The suppression of degree of dissociation of a weak electrolyte by adding a strong electrolyte having common ion is called as common ion effect. So a weak electrolyte is there, its dissociation can be suppressed by adding a strong electrolyte, and the strong electrolyte and weak electrolyte should have an ion, any ion which is common, so that the dissociation of the weak electrolyte will be suppressed. So let's take an example. Consider the ionization of acetic acid. So how does it dissociate into CH3COH, dissociate into CH3 COO minus and H plus, which is shown here. CH3COH dissociates into CH3COO minus and H plus. So now we are going to add a strong electrolyte, okay? Strong electrolyte which will be having an ion which is common to this. For example, let us take the strong electrolyte of HCl, okay? So HCl dissociates into H plus and Cl minus, right? So now as you can see, this is your weak electrolyte, this is a strong electrolyte, and in this you have the H plus here and H plus here, which is common. So this is a common ion, right? It is a common ion. Because of the presence of this common ion, the dissociation of the acetic acid will be suppressed. Now how this is happening, we are going to see now. So now applying the laws of mass action to this equation, right? How do we write the equilibrium constant? It will be the product of the molar concentration of the product raised to their powers divided by the product of molar concentration of reactants, right? Which are the products here? CH3CO minus, that is molar concentration of CH3CO minus and H plus divided by the molar concentration of acetic acid, right? So this is how you write the equilibrium constant equation, which we already know. So to this, a small quantity of CH3CONA, a salt, is added. So CH3CO minus ion increases. The concentration of CH3CO minus ion increases. So in order to keep the equilibrium constant K, making it a constant, H plus ion should decrease and CH3COH concentration must increase. So what we are going to add now? CH3COONA. So sodium salt of acetic acid, how does it dissociate? It dissociates into CH3CO minus and Na plus. So acetic acid, how does it dissociate? CH3COH dissociates into CH3CO minus and H plus. So now what we have added to acetic acid? We have added CH3COONA, which dissociate into acetate ion and Na plus. So now tell me, in this case, which is the common ion? Here also you have acetate ion, here also you have acetate ion. So the common ion is acetate ion. So now as we have added the salt, now what happened? The concentration of acetate ion has increased. So if the concentration of acetate ion has increased, to keep the equilibrium constant same, okay, this shouldn't change. If the concentration of acetate ion has increased, what should be done? The concentration of H plus should decrease, or else the concentration of acetic acid should increase, right? If this is increasing, this should increase, or else this should decrease, right? Okay, I hope it is clear. So that is what is written here. In order to keep the K constant, concentration of H plus should decrease and concentration of acetic acid must increase. So therefore, the degree of CH3COH is suppressed. The degree of dissociation of acetic acid will be depressed. Why? Because the concentration of acetate ion is increasing, right? So it can be also suppressed by adding HCl or any other strong electrolyte containing common ion. So as discussed, HCl can be also used to suppress this dissociation. So HCl dissociates into H plus and Cl minus, right? In that case, which will be the common ion? H plus will be the common ion. So if H plus is the common ion, then the concentration of H plus will be more. Right, what should happen? The concentration of acetate ion should decrease and concentration of the acetic acid should increase. So in that way also we can suppress. So I hope common ion effect is clear. Moving on to solubility equilibrium of sparingly soluble salts. So what is sparingly soluble and what is solubility, we are going to discuss now. So every salt has its characteristic solubility which depends upon temperature. So all of the salts are not able to be dissolved in all solvents present, right? And their solubility, that is how much extent it will be soluble in that particular solvent, will also depend based on different factors as well as the temperature, right? So on the basis of solubility, salts can be classified into three types. One is soluble, that is if the molar concentration of the salt is greater than 0.1 molar. Right, okay, they will be highly soluble. They are highly soluble, their solubility will be high. Next is slightly soluble, their molar concentration must be around 0.01 to 0.1 molar. Now next one is sparingly soluble, that is less than 0.01 molar. They are very, very less soluble, right? So this is the classification. In detail, we are going to study about the sparingly soluble salts, right? So in a saturated solution, what is saturated solution? Saturated solution means further any salt can't be dissolved, right? It is already saturated. More it can't be dissolved, right? Their solubility has attained its maximum. So the saturated solution of a sparingly soluble salt contains both ions and undissolved salt. Therefore, an equilibrium is established between both ions and the undissolved salt. It is called as the solubility equilibrium. Now, what does that mean? Let us take AB, which is the substance. It dissociates into A plus and B minus, right? So these are the ions which are formed. It is sparingly soluble. So what happens? A plus and B minus is formed. At the same time, A plus and B minus will be combining to form AB. The product AB will also be formed. So there exists an equilibrium between the undissolved substance. This is undissolved, and the ions. These are the ions and these are the undissolved substance. So there exists an equilibrium. Okay. So that is what is mentioned here, which is called as a solubility equilibrium. There exists an equilibrium between the undissolved substance and the ions. Now moving on to the next one, what is KSP? That is solubility product, or also called as solubility product constant. So what it is solubility and how to calculate it, we are going to see. So consider a saturated solution of again sparingly soluble electrolyte AB. It contains both ions and undissolved solute. Therefore, equilibrium is established between ions and solid, which we have discussed now. So this is the equation. This is your undissolved electrolyte which dissociates into A plus and B minus. So what happens at the same time? A plus and B minus combines to form AB. So there exists an equilibrium between the undissolved substance and the ions. So now to this we are going to apply the law of mass action. We have already studied how to write the equilibrium constant. It will be A plus molar concentration of A plus into B minus divided by molar concentration of AB. So now this molar concentration of AB we are going to take to the other side, that is K into molar concentration of AB is equal to A plus into B minus. So this much part is your KSP, that is solubility product. So what is KSP? It is K into equilibrium constant into molar concentration of your undissolved solute, which is equal to molar concentration of A plus into B minus. Okay, so this is your KSP. So this is a very, very important equation. Okay. So it is the product of molar concentration of the ions. So solubility product is equal to the product of molar concentration of the constituent ions raised to their appropriate powers in a saturated solution of sparingly soluble electrolyte at a given temperature. So it is the product of molar concentration of the ions, right? And it is raised to the powers which is equal to their stoichiometric coefficients if it is necessary. So we will see that. So the solubility product equation for different types of electrolytes we are going to see. So now that will be clear to you. So first will be AB2 type. So what is AB2 type? How does it dissociate? We discussed AB type, right? It dissociates into A plus and B minus. AB2 type dissociates into what? A2 plus, right? This is the charge of A2 plus and 2B minus, right? A2 plus and 2B minus. So how do I write KSP? KSP we have already discussed. This is a product of molar concentration of the ions, right? So is there any number of moles here? No. So it will be A2 plus, and here you have 2, right? So that will come as the power. So don't write the 2 here. It will come as the power which is shown here. Clear? Now the next one is A2B type. So A2B type, how does it dissociate? It dissociates into 2A plus and B2 minus. Right, this is how it dissociates. So how do you write the KSP? Again, there is a number of moles here. So it is A plus raised to 2. This will come in the power into B2 minus. Right. Now next is AB3 type. AB3 type dissociates into, AB3 type will dissociate into A3 plus and 3B minus, right? So that is shown here, A3 plus and B minus raised to 3. This will come in the power. Next one is AB4. You will have A4 plus and B minus raised to 4. Then you have A4B4, that KSP will be A4 plus raised to 3 and B3 minus raised to 4. So I hope it is clear. This is how you write the solubility product for various electrolytes based on their type, right? The next one is solubility product expression. Consider a saturated solution of a sparingly soluble electrolyte AB. An equilibrium is established between both ions and undissolved solute. So the same case we are going to consider here. You have an equilibrium existing between AB and its ions. So now let S be the solubility of AB. So here we have discussed how to write the solubility product. Now we are going to write in terms of solubility, right? So now S will be the solubility of AB. So it gives S mole of A plus and S mole of B minus. Okay. So S will be the solubility of A plus and S will be the solubility of B minus. So we can write, instead of A plus we write S, instead of B minus we write S. So KSP will be S into S, that is S square, right? So this is a relation between solubility product and solubility. So it is a solubility product expression for AB type of molecule. So different types you will get different solubility product equation, right? It is an expression which relates solubility and solubility product. So let's take another example, how to write the solubility product expression for different electrolytes which relates with its solubility, right? So AB2 type, again we have discussed AB2 type already. It dissociates into A2 plus and 2B minus. So KSP, how do you write? It is molar concentration of A2 plus molar concentration of B minus raised to 2. Okay, so now molar concentration of A2 plus, what is the solubility? It is S itself. So now the molar concentration of B minus, is it just S? It is not just S, it is 2S. Why? Because it dissociated into 2B minus, right? So you write 2S here and you have the 2 here which will be the power. So it will be S into 4S square which will give you 4S cube. I hope it is clear. Now moving on to the next one, A2B type, A2B. How does A2B electrolyte dissociate into? It dissociates into 2A plus and B2 minus, right? So KSP, how you will write? It will be A plus raised to 2 into molar concentration of B2 minus. So this will be A plus. What is the molar concentration of A plus raised to 2? It will be there. So solubility you have to write it as 2S, right? It will be 2S into, this will be S, and here in the 2S you have a power also. So again this will also become 4S cube. I hope it is clear. This will also become 4S cube. Now the next one, AB3 type. AB3 type dissociates into A3 plus and 3B minus. So here the solubility will be S itself. Here the solubility will be 3S and in the power you will have a 3 as well, right? So S into 3S cube, that will be 27S raised to 4. Okay. So this is a relationship which relates between the solubility product and solubility. I hope it is clear. So the next one is ionic product. What is ionic product? It is a product of molar concentration of the constituent ions raised to the appropriate power in any solution of an electrolyte. So it is similar to solubility product itself. So what is the difference? Let us see. So if ionic product is less than the solubility product, it is unsaturated solution, therefore the precipitation does not take place. Okay, so if the ionic product is less than solubility product, precipitation will not take place. It is still an unsaturated solution. Okay, now if both of them are equal, ionic product and solubility product is equal, it is just saturated solution, therefore precipitation does not take place. That means just now it has become a saturated solution. Now if ionic product is greater than solubility product, it is super saturated solution, therefore precipitation takes place. So this you have to remember, how ionic product and solubility product are related, and based on that how you can determine whether the precipitation will take place or not. So by this we come to an end to this chapter, equilibrium. So I hope the concepts that I've covered in this chapter is clear for you. So that's all for today. Thank you.